Hello. So today we're going to be looking at acid-base equilibrium and a specific problem in the Zoomdal notes as part of the PowerPoint for chapter 14 in the AP chemistry textbook. This is a fairly difficult problem, so we're going to go at it at length to make sure that you understand what's going on here. The question is fairly simple. It asks if the concentration of the phosphoric acid in solution is equal to 1.0 molar, find the concentration of the phosphate ion. So I've listed the question right at the top here. You can see it. And you'll see that the concentration has two sig figs over here, 1.0 molar. And it's asking for 3 dissociations. I actually wrote them down below. You can see the dissociations. And from there, you can look and see how each of them dissociates into the H+, or really the hydronium ion, combining with the water. And then the different ions, the anions that are formed as a result of the loss of the hydrogen. Now, the key thing to remember with these problems is that when you have a polyprotic acid like H3PO4, only the first dissociation, this one right over here, is the one that gives off the hydrogens that make it acidic. The rest of them do not give off hydrogens. They do, but it's very, very negligible. So when we're looking at concentration of hydrogens, we're only going to be looking at the concentration of hydrogens given off from this first dissociation over here, not from the second and third one. So we're only looking at the Ka1 value first of all. We'll need the Ka2 and Ka3 when we're looking at the overall PO4 3 negative concentration. But again, hydrogen ion concentration or hydronium ion concentration will be derived from the first Ka value alone. So the first thing you need to do to solve this problem is just remember the general rule that Ka is always equal to the products over the reactants. So if I were to write a Ka1, it would be the product H plus times the other product H2PO4 minus over the concentration of the reactant. In this case, the reactant is H3PO4. So that's going to be the generic formula. It's always the reactants on the bottom and the products are going to be on top. Now remember that we always have to account for coefficients as well, and coefficients and equilibrium constants are the exponents. But in this case, all of our coefficients are 1, so we don't have to worry about exponents for this problem. They're all going to be 1 to 1 to 1 ratios. Okay, so now that we know that, we're going to have to solve the first one. So let's do the first one right up here. We know our Ka1 is equal to 7.5 EE negative 3. This was given to us in the problem, and that's equal to, let's put in some of the numbers now. So the top numbers we don't know. We don't know how much H plus is made at the concentration, and we don't know either how much H2PO4 minus is made. But we do know that the starting concentration of the H3PO4 is 1.0, and we're losing off of that a certain amount, minus X. And whatever we lose off that amount, I'm going to simplify this and say that whatever is lost from the bottom is gained at the top. And we'll make sure we understand that in a second. So the formula that you need to know for this is this one. Now, why did I write it like that? Well, look at the balanced equation. You're always basing everything in chemistry off the balanced equation. It's this one right over here. So I'm telling you that I'm starting with 1. Think of 1 molar over here for my H3PO4. Some of it is dissociating into H plus and H2PO4 minus. So for every H3PO4 that dissociates, I get 1 H plus and 1 H2PO4 minus. If I have 5 of these, I get 5 H pluses and 5 H2PO4 minuses. If I have 2,000 of these, I get 2,000 of these and 2,000 of these. So that's exactly the same thing that's happening over here. Whatever I lose off of my initial one on the bottom, I'm gaining of that one on the top. So I'm gaining the H's on the top, and I'm gaining the same amount of H2PO4 negative on the top. So this minus the X is going to form the X on this side and the X on this side. You can see that also through an ice chart, but I don't really have the time to do that right now. If you want to make your own ice chart, you'll see the same exact result. So now we have to solve for this. And how do we solve for this? We're going to take this number over here, the 7.5 times 10 to the negative third, and we're going to multiply it by the 1.0 minus x. This whole entire thing is a factor being multiplied on both sides. So it'll cancel on the bottom of this side, and then it'll multiply the 7.5 e negative 3. So what I get, first of all, is the 1 times the 7.5 e negative 3. That gives me an answer of 7.5 e or e negative 3. And then the second part is the 7.5 e negative 3 times the negative x. This is a minus 7.5 e negative 3 x, and then equals, and then we have what's left over on the top here, x times x is x squared. Okay, so this is a little bit of a tricky one. The reason why some people may think that you're able to get rid of this x in the bottom here because it's negligible, the 5% rule proves otherwise. You'll have to account for it in this case. Sometimes in some problems, not in this problem, you will not have to worry about the x in the bottom because it's so small that we just neglect it and it makes the math a lot easier. In this case, you do need to do the quadratic formula. So if you simplify this, you're going to get an answer of x squared plus 7.5 e to negative 3x minus 7.5 e to negative 3 is equal to 0. Now, solving for this one with a quadratic formula, I'm not going to take the time to do this right now because it's a little bit lengthy, but I'll give you the quadratic formula. It's negative b plus or minus the square root of b squared minus 4ac all over 2a. If you did this, you'll get an answer of x equal to 0.082933. Now I kept several of the digits here because, again, remember, never do sig figs until the very, very end. By the way, on the plus minus for the quadratic formula, you have to use the plus. If you use a minus, you're going to get a negative answer over here, and you cannot have a negative answer. The change has to be a positive change. So you have to use the plus form for this one, and that gets you that answer. So now that we know that, we could go ahead and say that this is equal to x. So we also know that h plus is equal to that as well. And we also know that my PO4 negative is also equal to that, right? Because we have x, we solved for x, and we said x is equal to my h plus, and x is also equal to my H2PO4. Whatever was lost from the bottom one over here was gained on the top one. So for every little bit I lose from the H3PO4, I gained in H pluses, and I also gained in H2PO4 minuses. So this is how much I lost off the one on the bottom, and this is how much I'm gaining. So this is the amount of H plus I have, and it's also equal to the amount of H2PO4 minus that I have. Okay, so now let's set up the second one. That's the hardest step. Once you get that step, the rest of the problem becomes a lot easier. Let's look at the second Ka. The second Ka, let's choose a different color for that one. Let's do green. My second Ka over here is equal to 6.2 EE, or E negative 8. And this is equal to, my reactants is on the bottom, and again, my products are going to be on top. So my products are going to be on top, H plus, and in this case it's HPO4 2 minus, and my reactants on the bottom, my reactants for reactant for formula number 2 is H2PO4 negative. Okay, so now we can do a substitution because we have some of these numbers. So the H2PO4, I just said it's equal to this number right over here. So I'm just going to put this number right in here, 0.82933. Okay, and my H is also equal to this number over here, 0.082933. Okay, and we don't know the last one. That's the one, the unknown. HPO4 2 negative. Running out of space. Okay, so we have our answer over here, right? And all this stuff over here is equal to my 6.2 EE negative 8. 6.2 times 10 to the negative 8. So this is actually a very easy question. It looks very difficult, but it's not, because the number on the top here and the number on the bottom are exactly the same, so they cancel. This cancels with that. They cancel, so basically it sets us up with the final answer. Our final answer is HPO42 negative is equal to 6.2 E negative 8. Okay, we're almost done. One more step to go. We're going to use the last formula, the formula right over here, to figure out the concentration of the PO43 negative. So our last Ka, let's do it over here. We'll use actually a different color. Let's use blue. So our last Ka is equal to 4.8 EE negative 13. And in this case, that's equal to, again, my H plus, and then this time my product is PO43 negative, and on the bottom I have my reactant, which is HPO42 negative. Okay, so now let's solve for this one. This is the last step before we're done. Okay, so again, remember that the concentration of the H never changes. We said that all the concentration of the H is derived from that first dissociation. So my H concentration right over here, this 0.082933, always remains the same. So I'm going to put the same exact number over here. So my H concentration is 0.082933. My PO4 concentration is unknown, so that's the one we're trying to solve for. And then the last part on the bottom, we have the concentration of the HPO4 negative. We just figured that out right over here, right? So this concentration, HPO42 negative, is this one right over here. So I'm going to plug in this number, 6.2 E to the negative 8. Okay, so now we have all of our knowns over here, and we have all the rest as numbers. So we could easily use algebra to solve for this. And if you do, you get a final answer of PO43 negative equal to, and how you would do this is, first thing you would do is you'd multiply 6.2 E to the negative 8 times 4.8 E to the negative 13, right? So what you're doing here is you're multiplying this one right over here, 6.2 E to the negative 8 times 4.8 E to the negative 13. So when I do that in my calculator, I'm getting an answer of 6.2 E to the negative 8 times 4.8 E to the negative 13. Oops, let's do it again. 6.2 E to the negative 8 times 4.8 E to the negative 13. And I get an answer of 2.976 E to the negative 20. And then the last step is going to be dividing by this number right over here, this 0.082933. So divide that by 0.082933. So I have my final answer. Remember, sig figs count, so with my final answer. So because the starting number way back over here has 2 sig figs, I need 2 sig figs for my final answer. So rounding this to 2 sig figs, my final answer is going to be 3.6 EE negative 19. And again, this is units, capital M, because it's the molar concentration of the phosphate ion. All right, I hope you enjoyed today's lesson. Thanks for tuning in.